Welcome to This Explainer. Today, we're taking a seriously mind-bending journey from the micro to the macro to truly understand, arguably, the most mysterious objects in space. We're peeling back the layers of the cosmos to look at black holes. But don't worry, we aren't just going to throw around complex math here. We're going to visually break down exactly how they work, how they shape our universe, and, get this, why they might literally be the reason we exist at all. We're looking way beyond the dense equations to explore how these dark beasts might actually be the ultimate cosmic creators.
Okay, let's dive right in by busting the absolute biggest pop culture myth straight out of the gate. When you hear the words black hole, what's the very first image that pops into your head? For most of us, it's this terrifying, unstoppable cosmic vacuum cleaner, right? Just roaming around the galaxy, aggressively hunting down and devouring planets, stars, and whatever else gets in its way. But, yeah, that is simply not true.
Instead of a vacuum cleaner, I want you to think of a black hole more like a giant cosmic waterfall. If you're paddling a boat far upstream from a rushing waterfall, you're perfectly safe. You just paddle along normally. It's really only dangerous if you let yourself drift too close to the very edge of the rushing current where the water violently pulls you down. Well, gravity works the exact same way. If you're far away from a black hole, you just orbit it peacefully, exactly like the Earth orbits the Sun. Actually, fun fact, if our Sun was suddenly magically replaced by a black hole of the exact same mass, we wouldn't get sucked in. No way. We just keep orbiting completely normally. You're completely safe unless you drift too close.
So, that physical edge of our cosmic waterfall, it has a name. It's called the event horizon. It is the absolute definitive safety line. Once you cross that event horizon, the pull of gravity becomes so unimaginably strong that not even light, the absolute fastest thing in the entire universe, can paddle fast enough to escape. And because nothing can travel faster than light, that boundary really is the absolute point of no return. Anything that crosses it gets completely squished and basically becomes one with the black hole forever.
Now, what's really interesting is that humanity didn't always call them black holes. The name itself has this fascinating evolution. Back in the 18th century, a thinker named John Michell used math to imagine a star with gravity so strong that light would literally fall back into it, and he called it a dark star. Sounds kind of poetic, right? Fast forward to the 1930s, and J. Robert Oppenheimer, yes, the exact same Oppenheimer who later built the atomic bomb, studied these incredibly dense objects. He gave them a very dry, highly literal acronym, GCCO, which stands for Gravitationally Completely Collapsed Object. Catchy, huh? It actually wasn't until the 1970s that physicist Robert Dicke popularized the term black hole. He was drawing a really dark, evocative comparison to the infamous hypercrowded 18th century prison known as the Black Hole of Calcutta. And honestly, it perfectly captured that idea of extreme, inescapable density.
And when we say extreme density, we really mean it. Just imagine taking hundreds of millions of tons of matter, picture massive mountain ranges or entire fleets of aircraft carriers, and crushing them down until they fit onto a single teaspoon sitting in your kitchen. That staggering, massive number is what just one single teaspoon of a black hole would weigh. To put that into perspective, it proves that a black hole's immense terrifying power comes entirely from its extreme density, not just its physical size. It's all about taking a massive amount of material and crushing it into an impossibly tiny space.
Which brings us to a really great question. How do you even make something that unbelievably dense? Well, it starts with a star. Throughout its life, a massive star is engaged in this brutal, epic tug of war. On one side, you have the sheer, crushing weight of the star's own gravity, which is constantly trying to pull all that mass inward. But fighting back from the inside is the extreme, violent heat of nuclear fusion, millions of degrees of energy pushing outward, keeping the star inflated and stable. For millions of years, it's this perfect stalemate, but eventually, the star runs out of fuel. The outward push stops, and when that happens, gravity wins the ultimate victory, causing an unstoppable, crushing collapse that leaves behind a black hole.
But the death of these massive stars leaves behind a pretty profound cosmic mystery. When we look out into the universe, we clearly see two main types of black holes. We have stellar mass black holes, which are about 10 to 20 times the mass of our Sun, and then we have supermassive black holes, which sit at the center of galaxies and are millions, sometimes billions of times heavier than our Sun. But much like human evolution, we're missing a crucial step here. We see the small ones and we see the giant ones, but the intermediate, middleweight black holes are incredibly rare to find. It's literally an evolutionary missing link that has astronomers completely baffled.
And speaking of those supermassive black holes, they introduce the absolute ultimate cosmic chicken and egg problem. Did a bunch of stars cooperatively gather together to form a galaxy and eventually spawn a massive black hole right in the center? Or did the massive black hole form first, acting like some kind of cosmic mob boss that pulled all the surrounding stars into a massive galactic empire? Well, recent, completely mind-blowing data from the James Webb Space Telescope looking at the very dawn of the early universe suggests these massive black hole bosses might have actually formed before the stars themselves. So the black holes might be the foundational architects of the galaxies, not the other way around.
Now, to truly understand what happens if you get near one of these cosmic bosses, we've got to remember Einstein's greatest rule. Massive gravity literally slows down time. Space and time are fundamentally connected into this fabric we call space-time. The stronger the gravity, the slower time ticks. Actually, as an incredibly fun fact, this means that if you study for an exam on the first floor of a building, closer to the Earth's gravitational pull, you technically experience a fraction of a nanosecond more time than if you studied on the top floor. Crazy, right? Now, as you get closer to the extreme gravity of a black hole, that stretching of the clock is magnified billions of times.
And because a black hole bends space-time so aggressively, it plays absolute tricks on light. This step-by-step breakdown explains exactly why the famous movie visualizations, like the breathtaking ones we saw in the movie Interstellar, look like a glowing folded bagel. Basically, a black hole is usually surrounded by a flat disk of glowing, superheated gas called an accretion disk. But the black hole's gravity is so intense that it bends the light coming from the back of that disk, folding it entirely over the top and underneath the bottom so it shoots straight into our eyes.
We could actually call this visual illusion space-time cubism. Think about it. Just like Pablo Picasso painted portraits where you could uniquely see the side and front of a face at the exact same time, a black hole uses gravity to paint a Picasso-like picture of the cosmos. It's aggressively bending light from the back, the top, and the bottom of the disk, and projecting it right in front of your eyes all at once. It's honestly one of the most stunning, mind-bending visual illusions in the entire universe, and it's crafted entirely by the sheer force of gravity.
And we know this isn't just a mathematical theory, because humanity actually achieved the impossible. We actually photographed the silhouette of the M87 supermassive black hole in 2019. But capturing it was a monumental, awe-inspiring task. I mean, the black hole is 50 million light-years away. Taking a picture of its glowing shadow required a network of telescopes across the entire globe, acting together as one massive Earth-sized lens. To put that level of precision into perspective, it is the exact equivalent of standing on Earth, looking up, and successfully photographing a literal donut sitting on the surface of the moon. Capturing that donut-shaped shadow was so important because the sheer footprint of these supermassive black holes is just staggering. So the crucial point here is that while the singularity itself, the very core of the black hole, has literally zero physical size, the event horizon footprint around it can be absolutely massive. If you drop the supermassive black hole at the center of our Milky Way into our solar system, its dark horizon would easily swallow the entire orbit of Mercury. But M87, the one we miraculously photographed, its horizon is so profoundly large it would comfortably swallow the entire orbit of Pluto.
Now, despite all this world-swallowing power, physicist Stephen Hawking made a groundbreaking discovery. Black holes actually have a weakness. They aren't immortal. Because of strange microscopic quantum effects happening right at the edge of the event horizon, black holes leak tiny particles. This means they actually have a measurable temperature and aren't completely black. Over trillions and trillions of years, they will slowly evaporate and fade entirely into nothing. This is incredible because it's one of the very few places in physics where the rules of the incredibly massive, general relativity, and the incredibly tiny, quantum mechanics, actually unite perfectly in one single concept.
And this intersection of the massive and the microscopic leads us to the ultimate mind-bender. Think about this for a second. If the math of a black hole describes a single point of infinite density, doesn't that sound oddly familiar? Because it's the exact same math we used to describe the Big Bang, the explosive birth of our universe. This led physicist Lee Smolin to propose a truly fascinating theory. What if the incredibly dense singularity inside a black hole and the explosive spark of the Big Bang are actually the exact same thing?
Which leads us to the breathtaking theory of cosmic natural selection. It suggests that every time a black hole forms, it doesn't just destroy matter. It might actually birth a brand new universe inside itself. Think about it kind of like Charles Darwin's biological evolution. Universes that happen to have the perfect physical laws to create good gravity will successfully form more stars. More stars eventually mean more black holes, and those black holes birth more universes, passing on those good physical laws to the next generation. It essentially creates a cosmic Russian nesting doll situation, a matryoshka doll of infinite universes, one inside the other. And honestly, it perfectly explains why the physics of our universe are so flawlessly balanced to support stars, planets, and ultimately, us.
All of this brings us to one final, absolutely staggering question. If every single black hole in the cosmos is pregnant with a brand new universe, whose black hole are we living inside right now? We'll leave you with that provocative thought to ponder the next time you look up at the night sky and feel like cosmic dust. Thank you so much for joining me for this explainer. Keep looking up, keep asking those big questions, and I'll catch you next time.